Okay, so welcome all. Today, in this talk, we're going to have Professor Nelson Amaral from the University of Alberta. Professor Nelson is well known in the compiling technology area, has done a very interesting research in many code optimization techniques for compiling technology. So, welcome, Nelson, and please go ahead.
So today I'm going to tell you about a piece of work that we finished recently that we still have it under review. And if you look at the title of the slide, the topic says a convolutional algorithm that eliminates unnecessary copies and uses standard numerical library microkernels. So I think the best way to go about this talk is to start looking at what this title means, right? And let's start to talk about the convolutional algorithm first. And when I teach, I like to start with something that I expect you to know. And I expect that you know a little bit of this brief history. So if you recall, it was as recent as 1998 that Jan LeCun and colleagues proposed that we could use this gradient-based learning to recognize documents. And then, in this brief history, we have Alex Krishnevsky, then together with Geoffrey Hinton, using this to build ImageNet, that is the piece of machine learning, deep learning, that can recognize or classify images based on this convolutional network. Then the next piece of history that we want to recall is Café, which appeared as an archive paper in 2014. And what Café does is to give us a way to compute convolution by transforming it into a general matrix multiply. And what it does is to do this transformation that we call an image to column transformation that allows us to then use a generic matrix multiplication. So one of the things that I need you to do first for me is to be convinced that the convolution is important. That's the problem that we need to solve. And one way to do that is to look at the percentage of time that you typically spend on convolution when you are doing either a propagation in the network, either training or lookup. And you see all these big parts of the graph here are convolutions. So if you want your convolutional neural networks to be fast, you have to make convolution fast. The other thing that I want to draw your attention to is that we're going to be doing convolution on CPUs, not on GPUs, as you may expect. And the reason that we're doing that is that the prediction is that in about 2025, this prediction is a little bit older now, it's from 2019, and this 50% now the prediction is a little lower, but it's still a significant percentage of all the convolutions that will be done in CPUs. And more recently, companies like Intel, ARM, and IBM have introduced matrix multiply accelerators into their CPUs for a very good reason. Because sometimes, because of security, you don't want to send your credit card data to a separate accelerator in order to do an inference, for example. So even though you may use a set of GPUs or accelerators to do your training, in some training data, if you can afford to transfer the training data somewhere else, you're not going to be able to do your inference outside of the memory space that you have all your security. So this is to tell you that we're going to be doing convolution on CPUs, and we work with these 4 different CPUs in this work. So let's first think about convolution and what convolution is. This is an animated slide that should be very useful for us to understand what convolution is. So there is an input tensor that typically think of it as an image, but could be anything, actually, any kind of tensor. And then there is a set of filters. And what we're going to do, we're going to take the filter and we're going to multiply the filter by one segment of our input tensor. and that will give us, and then we're going to add the values, and that will going to give us one value that we're going to have in our output. So typically, the application that we think about would be that this input tensor is an image, and those filters may represent things that we know, like dogs and cats and hot dogs, etc. And then with an appropriate set of filters, the convolution here generates something that we don't know what it is. But the magic is that if we keep doing this a number of times, eventually we can come up with an answer about this original picture that's something that we care about. That's pretty much is the magic of the convolutional neural networks, but the most important thing here for you to remember is what convolution is doing. Convolution is doing the multiplication of this smaller filter over this large tensor, and it's using many of them. So I told you that one of our goals is to eliminate these unnecessary copies. So what are those unnecessary copies? So let's look at what the problem that we have with the image to column approach. In an image to column, what we have our filters here that we're going to apply, and we have our input tensor. The way we are able to use the standard matrix multiplication to do convolution is by transforming this input image into what we call this series of column vectors. We create a new tensor, and the way we create this new tensor is by taking one of the windows here where I'm going to apply one of my filters and transform the elements from that window into a column in this new tensor. Once I have done that, then I can do some kind of transformation in this input tensor, taking, for example, that band, that vertical band there, and I can multiply it by this horizontal band, and this will be a standard matrix multiplication that I'm doing to obtain one part of my output. So I can do a sequence of matrix multiplications if I need to do this. So what we have here is, on the upper part, I have the image to column, and in the bottom part, I have the gem. So when I was discussing, and several of us were discussing how to do it better with Ivan, who is the student that did that, the idea was, we should combine the image to column transformation with the gem transformation, because what happens in gem is that the most efficient way to do a matrix multiplication is to do an operation that we call packing, where we're going to take portions of the matrices that we want to multiply, and we're going to change the order of the elements so that we increase the locality. Because we have an n-square algorithm, what happens is that if I do a transformation in input data once, I only pay that cost one time, and now I do multiple access to that data. That is the idea. So the idea was, let's combine the two, because what's happening here is silly. We are doing one copy of the data and then doing another copy of the data. And then we thought that we had a brilliant idea. So then I went to look into the literature, and we were not the first ones. Several people have done that before. So we went to the typical cycle of a master's student thesis, say, okay, we don't have a solution, we need to start thinking again. And then I went to look, but wait a minute. Look at how image to column is doing this copy. And image to column, did you notice that there are 9 copies of 13 in this tensor? And there are, I think there are 8 copies or so of 14 and so. So there are multiple copies of the same element. And I will say, this is a waste. We should not need to do that. So those are the redundant copies, or the copies that are not necessary. The next thing that I told you in the title that we're going to try to use is standard numerical library microkernels. So the numerical libraries, let's talk about those. So the numerical libraries, they follow a standard that's called the basic linear algebra subprograms. What the BLAS is not an implementation. BLAS is a specification of how this library should be built. And then there are several implementations of BLAS. For example, one implementation of BLAS is called BLIS. That is the BLAS-like library instantiation software. And what we're going to see in one of those is something like this, that is the specification of how you do the computation of two matrices. But typically what happens in this microkernel is that the size of the matrix that you're going to multiply are fixed. The reason for that is a very clever way to divide and conquer. What we're going to do, we're going to take these fixed size blocks of the matrix, that will be our microkernel, and we're going to match them with the hardware. So if Intel is building a hardware that has a given size, we're going to build a microkernel for Intel that matches the hardware. Now, if you have a problem that you have to multiply a much larger matrix, there's another layer that will come before the microkernel that we're going to break these larger matrices into the smaller pieces so that they can use the microkernel. So the question now is why I'm using the microkernel to do my computation of the convolution. Because when a company comes up with a new hardware accelerator or a new way to do an operation like this, the company typically will not going to invest into the compilation tool to do the use of these new instructions, for example. The company will put some of their best engineers to hand code the solutions into these microkernels. So these microkernels are heavily hand optimized for each one of the manufacturers. So if we can target them, we are riding this wave, right? We are benefiting from all the investment that is done by the companies if we use the standard microkernels. And remember that I told you that I want to eliminate these unnecessary copies. So how do I eliminate the unnecessary copies? For that, we're going to talk about our solution that is the convolution solution. We call it YACONV for yet another convolutional algorithm. So I have my weights in there. That's my filters. And here I have my input tensor. What I'm going to do now is the first thing that I'm going to do is to change this input tensor to be a column major order instead of a row major order. And the beauty of this is that I don't need to do any operation to do that. I'm just looking at the tensor in a different way because I'm going to be moving this data soon. So I don't need to do a transpose and then a move. I'm going to do the move thinking of this as column major order. And then I'm going to pack this input into L3. Sorry, the slide is cut off here for now. In a way that I'm going to have the data in the order that I need it to be accessed for the computation. And then I'm going to pack the filters into an L2 buffer. So I play with the memory hierarchy that I have, but remember, I'm doing that in CPU. So you may be wondering, what do you mean you're going to put something in L3, you're going to put something in L2? You have no control over this in the machine. The way I do it is by the order in which I access them. Of course, when I package this into L3, the data is going all the way to the L1 and occupying the L2 as well. But then later, when I come and I pack the filters into that I want to be in L2, the data that I had put in L3 is going to have been kicked out. Right? So by the order in which I access these elements, I am playing with where they will be in the memory hierarchy. So, and then I can now do my matrix multiplication between this packet filters and this packet input in L3, where I did not do the additional copies for the image to column transformation, and I'm going to get my output. The price that I have to pay is because I'm using a standard matrix multiplication in the way that I format my data. The data that I actually care about is spread in my output. There are things in between that I don't care about that are actually also get computed. So I have a cost to pay now that I need to do a gather in the end to bring things together if I want my output. However, if I'm going to use this output as the input for the next convolution, I don't need to do the gather. Because remember, the first thing that I'm going to do for the next convolution is to do a gather to put the data in the order that I need for the next convolution. So I have that advantage there. So the details of this is in the algorithm. If you care about this, it is in the paper. You can look at the details to see how this works. But that's pretty much the trick that that Ivan came up in that work. So what happens here is that any change that happens on the top only happens one time, and what happens down here happens in a loop. So let's try a different representation of the core ideas. Perhaps it will be easy to understand. What I did here is I create a cartoon of the memory hierarchy of the latest Intel processor. So this is my L3 cache, this is my L2 cache, and this is my L1 cache. And they are drawn in proportion to their sizes, so that you can build in your mind an idea of how big these things are. And what I'm going to do, I'm going to pack my input image into L3, and notice that I cannot use the entire L3. I need to save space in L3 for other parts of the computation that may need space there too. That's going to happen in all levels of the hierarchy. I always need to leave space for everything else that needs to be resident in that area of cache, so that I don't end up kicking things out that I don't need to. So that's where I'm going to pack my input image. I'll pack my filter elements in L2, and I'm going to also leave a little bit of space in L2 for other things that I may need while doing the computation. And then what I'm going to do, my loop is going to be taking one small portion of my input image that will be packed in the order in which the elements will be accessed, because I planned to that and I changed the order of the elements already. And we'll bring that to L1. And then I'll do the operation between the L1 and the L2 here. And then when I'm done with this chunk, I get another chunk from L3 and I bring up there. That is how it actually works. And of course, I need to plan it carefully so that I leave all the space that I need in each one of the levels of cache, the rest of computation. If I am in a multi-core machine that has shared tenants in a certain level of cache, our solution is to simply divide that level of cache by the number of cores and assume that that's the amount of cache that we have for a given core in the machine. So the idea is here that we assume that all cores are doing the same thing. I don't know any other better solution to deal with the issue of having multiple cores accessing the same cache. So to give you a sense of performance, let me just give you some data here, and I'm going to give you three things. I'm going to give you the number of branches that each one of the algorithms execute. I'm going to give you the number of L1 data cache loads that each algorithm has to perform, and I'll give you the number of gigaflops that I obtain with the algorithm. The reason why we picked those two things to show in this graph is because they were the most relevant. Of course, we measure a number of different metrics when we are evaluating this. So here's the data, and you may take a little bit of time to understand the data. First of all, green, higher is better. The more gigaflops I have, the better my solution. And in blue, lower is better. The fewer L1 cache loads that I perform, the better. And the number of branches too, having fewer is better. So let's start where we do very well. Let's start on the right-hand side of the graph. Here we have a significant improvement over the image-to-column algorithm. And you see that I do much fewer L1 cache loads and much fewer branches. In here, on the other end, when we don't do very well, you can see that is the opposite. There's not a great correlation, actually, with the number of branches and the performance. Now, we're worried about this. What's going on in this area here? So first of all, I did not tell you what are the things in the x-axis. Those are all layers that I have from PyTorch networks. So these are real networks, real layers from PyTorch that I'm using. So what happens here is in some of those real layers, we are worse than the original algorithm. In a number of them, we are much better. So we want to understand what's going on. And to understand what's going on, what we did is to, so the other thing that I've given you here, this is plus 24% so that you have an idea of how good the solution is when I'm doing better, and this is minus 60% to see the reductions. So now what we're going to do is something different. We're going to ignore PyTorch and the layers that are actually used to do something, And we're going to artificially create different sizes. We're going to make we're going to vary h and w, but we always make them square. So all the tensors will be square. And as we change that, we're going to look at the number of L1 cache loads, the number of TLB loads, and the number of gigaflops. And we use this type of graph where I have this heat map. And for gigaflops, remember, I want the values to be higher, right? And as I start with small numbers here and I keep increasing, I'm getting better and better and better, right? And then I get to a point and I fall off a cliff. And the same pattern happens again and I fall off a cliff. And the same thing now if you relate that with what is going on to the TLB loads and the L1 cache loads, you're going to see that the colors are the opposite, right? When I have more L1 cache loads, my performance gets worse. But the point is that there are sizes here where I don't do well. And we could understand when we look at the algorithm what's going on. It has to do with the geometry of the caches inside. So the solution that we propose is that if someone wants to always win, it's very easy for you to check the size and decide whether you're going to use our algorithm or whether you're going to use the other algorithm that does better for that size. Because you can pick one or other algorithm for any one of the convolutions. So this work was done by Ivan Korostelev, who is a master's student from Russia. He has graduated now. And in this work, we use the unchanged gem microkernels, as we promised. We have integrate domain-specific packing into the gem so that we can improve performance. And we avoided the necessary copies that were done previously by the image-to-column algorithm. So this is what I had to tell you about the convolution. But as I have your attention in a few minutes, I can't resist by telling you about some other news. And the other news are some other interesting work that we have recently completed at University of Alberta. So one of them is the work that Kyle, Nathan, and this undergraduate student Yufei helped during the summer. That is generalized packing compiler analysis. So the idea here is that packing is something that has been done for a very long time for matrix multiplication. The idea of packing is the idea that we take the elements and we reorder them to have better cache behavior. I proposed about a year ago that we should be able to use packing for other things other than matrix multiplication. If we get an algorithm that has a loop nest and it's accessing several different tensors, I should be able to also do packing without even knowing what the algorithm is doing. So the idea here is that we're going to do a modular transformation that analyzes any piece of code and decides whether I should pack or not. So first let's recall the idea of packing and tiling. I already told you about that, but if I multiply into large matrices, what I do, I cut the matrices into small blocks. We call that blocking. And then I decided the order in which I need to access the elements in these blocks in order to do the multiplication. And I do the packing, and the packing is simply copying in memory the data, changing the order of the elements. That's what packing is. So of course there is a cost to packing, right? And if you think about cache behavior, the action of packing has very poor locality because I need to go all over the place to find elements that I need to put them together. So I can only do packing if the overhead of packing pays off during the computation. So what are the ideas in this work here is that I want to do this modular strategy in a compiler framework. Previous work on packing did not take TLB into consideration to decide. TLB is the translation look-aside buffer that's used to translate pages from virtual to physical address. And we have a cache for the translations that's called TLB. The performance of that cache was not taken into consideration in the past, even to decide the sizes of the blocks that we're going to pack. We take that into consideration. we remember that I told you when I was doing the packing that I need to leave enough space into a given level of cache so that other things that need to be there can also be there. So that's the idea of cache residency. So I decide whether I have residence. The other thing is that if I am accessing multiple tensors in a loop, should I pack all of them or a few of them or just one of them? So we make that decision as well in our algorithm. And so one way to put this is that we have an analytical model that we're going to decide when, what, when, and where to pack. So let's see if we look at a concrete example that's very simple, if we can understand what we're talking about. Let's consider that you have this computation that is, a 6-level a loop with 6 levels of nesting, and that access these 3 tensors that you see in the one statement that the loop has. So the question of what is, which one of those tensors should I pack? If I should pack any one of them. The question of where is, if I decide to pack any one of them, in which level of the loop nest should I place my packing operation? And the question of when is it profitable? I'm going to have a profitability analysis that tells me whether I should pack or not. Remember, this is being done by the compiler with no consultation with the programmer whatsoever. So the compiler has to analyze all that. So in the idea of, so these are the questions that are going to be answering there. And this is implemented in MLIR. That's this modular intermediate representation that is used on top of LLVM. So it's available to everybody. It's open source. So here, I'm not going to spend much time with data in this paper. This is a separate talk. But I'll give you one example. So here is the blue bars here. The blue band in the graph is for each tiling size. And remember that our packing algorithm does not decide the tiling size. The tiling size is decided by another part of the compiler. But so we can look at all different tiling sizes. And we can look at what happens if I do one individual packing only. What is the lowest and the best that I can have? That's the blue bar, the blue band. The points that we have here are the points that our algorithm found for each tiling size. And you can see the speed up over Polymer, which is the standard compiler that we have to compare with. Okay? So we can get significant speed up by doing the packing the way we are doing. So one thing that, so I don't know if you guys noticed, but Kyle is a former student of Guido Araújo from Unicamp. And someone else that we have that from Unicamp is João Carvalho. And João has participated in pretty much every research work that I have done in the last couple of years. So I just wanted to make sure that you know that we have a former PhD student from Unicamp that is very involved in this. And another thing that if you don't know of and you're interested in this area, you should know about kernel failure. That is a pattern matching solution that João created together with a number of co-authors, and you see some of the names here, including Guido Araújo and some of our collaborators from IBM. So that's the other piece of work that I want to give a shout out in case any one of you may be interested. So that's what I have for today. Thank you. Thank you.
Thanks a lot, Nelson. Any questions, folks?
Yes.
Go ahead.
In this part of the proposed convolution, you pop the data to cache, and as I got the thing to optimize that makes the optimization is handling the cache.
Mm-hmm.
And there is this part that you have a result of computation, part of the results are not used, you need to select the parts that are the result of action, the result of computation. And then you mentioned about keeping in memory as part of this result to be used later.
So if you have a convolutional neural network, what's going to happen is that you do one layer of convolution, and when you finish that convolution, you're going to do another convolution, right? So it's a sequence of convolutions.
You are referring to a single step of the convolution of the convolution through the entire matrix.
The convolution to the entire matrix. We take an input tensor, we take a collection of filters, and we do a convolution. And that produces another tensor. So a typical solution that then we're going to take this tensor, and we're going to do another convolution, right? So what is the output of one convolution is the input of the next. Okay. So if that is what I need to examine for some reason, I need to do a gather of that, the way I produce my output, right? But what I'm about to do is to use for another convolution, a possible implementation is that I know that the output is spread, is not contiguous in memory. So instead of gathering it all together and now reorganizing for the next convolution, I can do that in one step.
Leave there.
And then when I do my next algorithm or my next step, I can just do my gather from that spread data so that I avoid moving the data more than once.
Another question is it available in code?
Yes, the Yacon code is available. It is available. I can provide you the code if you want. But remember that the implementation that we have is for a single layer of convolution, right? It's not an implementation for a convolutional neural network. It uses the layers that we extracted from real networks, but our demonstration of the algorithm, it does a convolution for a single layer. Okay? It has not been integrated, for example, in PyTorch. Right?
You just answered my question. I was about to ask how was your experimental setup?
No, I hope that someone does, but it's not our job.
Okay. Yeah, right? Sure. You prove it.
It's there. It's there. Anybody can use the code that has been written, but it's not our job to do that integration.
Yeah, it's not our business.
It's not our business.
Okay.
Yes, Victor?
I know it's not the main focus of this talk, but on the packing paper, you talk about what to pack, where, and when. But what about how to pack? Is it the same packing every time?
The how to packing depends on the order in which the elements are being accessed. So the how to pack is determined by whatever is the algorithm that the programmer wrote into the code, right? We are not changing the order of the loops. Okay? That's another optimization that can be done, and usually is done ahead of time before we get there. So we allow the compiler to change anything that the compiler wants first, and then we assume that this is the order in which is the best order according to some previous optimization. And now we're going to pack. Because that's something that compilers do not do. They do not pack.
You mentioned that you compared against Polymer, right?
Polymer, yeah.
But where did you implement your solution? LLVM? Or
LLVM in MLIR, actually.
MLIR, yeah.
MLIR. That's the layer above LLVM.
So you need the compiler to do all the loop optimizations before what you do, right?
And that is part of the
Part
solution.
of the solution.
And LLVM may do other optimizations after that. But, that's where we separate.
Right.
But the idea of MLIR is that a number of the optimizations that were previously done in LLVM should migrate to MLIR because it's a higher level.
Yeah.
Okay, any additional questions, folks? No? So let's thank Nelson again. Just remember that
He's on, right?
Yeah.
But I think, oh no, I think he is, I don't know. Thank you for coming. Nice meeting you. Let's not do one of those hot mics kind of things, right?
Yeah.
Let's not do one of those hot mics
Yeah.
that the politicians do sometimes.
So I do that.
Maybe Uma coisa que talvez isso do código possa achar no website.
Me manda um e-mail, tu pode me mandar um e-mail que daí eu pego direitinho do Ivan. Porque o paper está under review e a ideia é que na versão final do paper a gente vai ter o link.
Ah, tá. E aí é coisa assim, implementada em C e usa essas bibliotecas de numéricas e roda. E você falou de uma camada só, um layer só?
Sim.
Seria...
O Convolutional Networks tem vários layers, cada layer é uma convolução.
Certo.
Então, para integrar isso, por exemplo, no PyTorch, você teria que integrar com todo o código do PyTorch, de forma que ele vá selecionar o nosso algoritmo no lugar de selecionar a image to column. Isso a gente não fez.
Certo. Mas o que você falou daquilo de salvar